My name is Esther Mahali, and for my project, I designed an oscillator system that regulates hormones that are responsible for our feelings of hunger and fullness in order to help patients with obesity manage their appetite and attain long-term weight loss. Obesity is notoriously difficult to overcome, in large part because our bodies have evolved an innate homeostatic system that activates changes in appetite and energy expenditure in order to promote weight gain and to make it very difficult to maintain sustained losses in body fat. A review of 200 papers describing dieting and exercise regimes concluded that these programs did not achieve long term weight loss. However, a promising line of treatment involves taking advantage of the appetite controlling hormones that underlie obesity. Two hormones that are especially significant are leptin, a hormone that makes you feel full, and its complement ghrelin, which makes you feel hunger. The inhibition of ghrelin in animal models has actually been shown to reduce food intake and body weight by means of a reduction in appetite and a modification of energy expenditure. So my device builds on this concept, but instead of implementing a constant inhibitor of ghrelin, my patients are able to retain some of their normal fluctuations in appetite by means of a timed oscillator system. So the device itself is a repressilator, and it oscillates between releasing an inhibitor of ghrelin called NOXB11 and an inhibitor of leptin called SOCS3, allowing the patient to feel alternatively full and hungry. However, the device will spend the majority of its oscillatory period inhibiting ghrelin, which would mean low SOCS3 and high NOXB11, and will oscillate to the active ghrelin or the hunger phase, which would be high SOCS3 and low NOx, only once about every 40 hours. Furthermore, the circuit is responsive to the contents of the most recent meal consumed. So, for example, if the patient has recently eaten an especially large or calorie-heavy meal, the resulting high sugar levels in the blood will repress the activity of sugar, which is a sugar-inhibited repressor first discovered in a bacteria species. So therefore, through a brief signaling cascade, the elevated levels of sugar in the blood will increase the expression of NOx, enabling the circuit to continue to repress ghrelin and to prevent overconsumption. So this part of my gene regulatory network represents the ring of repressors. You can see that the production of SOCS3 is coupled with the production of CI, and CI will then go on to inhibit the lambda promoter that is responsible for transcribing NOx. And again, the production of NOx is coupled with the production of LAC-I, and LAC-I will inhibit the LAC operon near the promoter that produces TET-R, and then TET-R will complete the ring by going and inhibiting the TET operon near the promoter that transcribes SOCS3. The remaining portion of my gene regulatory network is related to the production of sugar. Like I said before, sugar is not endogenous to the body. It's a bacteria. It's a repressor from a bacteria species, but it is constitutively produced from my device. So once sugar levels in the blood are elevated enough, the activity of sugar is inhibited and it can no longer repress the production of NOx. So NOx can go on to inhibit ghrelin and prevent overconsumption. It's important to note that this region of DNA transcribing NOx is separate from the region of DNA you saw in the previous slide. And this is because otherwise, when sugar levels are low, sugar will be inhibiting all sources of NOx and the oscillator will not be able to function. So my device will be implemented in a bioengineered organ based on the artificial pancreas designed by BioHub. In short, the cells expressing my DNA constructs will be surrounded by a biocompatible outer layer that allows the diffusion of nutrients and my repressors in and out. And each cell will be coated in a thin polymer coating to shield them from the effects of the immune system. So I modeled my device in MATLAB's Biosystems program, which was pretty straightforward, and here you can see my compositors. And here you see my constants, including rate constants and degradation, transcription, and translation rates. Most of these values were taken directly from literature sources, but I did have to modify some of my rate constants and my binding and dissociation constants in order to achieve the optimal oscillation dynamics of the circuit, particularly to get long periods of oscillations on the timescale of many hours. And here are my results. The graph you see here is what the oscillations would look like with low levels of sugar in the blood. So this is before sugar starts repressing the production of ghrelin. So my device was successful in that it produced short, sharp spikes of ghrelin with a max concentration of 4.4 nanomolar and a period of almost 40 hours. So you would only get a spike of ghrelin about once every 2 days. The maximum value of leptin was almost twice as high at 7.2 nanomolar with the same period. Optimally, the device would have achieved elevated plateau regions of leptin in between the ghrelin spikes in order to really help the patient feel full for most of their day. However, a resistance to the effects of leptin is actually a well-known facet of obesity, so it could be that while inhibiting ghrelin, except for a very short spike once every 40 hours, will have a very positive effect on regulating appetite, the sustained levels of elevated leptin might not even be a necessary component. And here's what the graph would look like when there are elevated levels of sugar in the blood. It's not very realistic because this is assuming that you have elevated levels of sugar for many days at a time, but it does give you an idea of how the concentration of ghrelin would change. So as you can see, leptin's oscillations remained unchanged, but the max value of ghrelin is halved at 2 nanomolar, and its period is very slightly shorter at 38 hours. So while it would be ideal if ghrelin's concentration dropped even closer to zero, it does show that this version of the circuit is responsive to the levels of sugar in the blood. So in both the ghrelin and the leptin oscillations, I noticed this odd plateau region that formed before their concentrations dropped entirely to zero. I'm not sure exactly what's causing it. It could be a dynamic of the repressolator ring, so it might be useful to try other oscillator circuits and genetic constructs. Another possibility would be that it's due to some steady state relationship that's being reached between the production of the repressor, NOx or SOS3, and its binding to its hormone, leptin or ghrelin. Maybe it takes some amount of time before enough repressor is produced to completely inhibit the hormone. And this could be resolved by increasing the production rate of the promoter from which the repressor is transcribed. So in terms of feasibility, I did have to make many assumptions about my binding and dissociation rate constants. And if I couldn't modify existing repressors to match my ideal values, it's very likely that the timing of the oscillator would not be preserved. In addition, designing my bioimplantable device to have optimal diffusion and immune-resistant qualities wouldn't be a trivial problem to solve. And finally, a more sophisticated version of my device would account for circadian rhythms to avoid undesired food cravings in the middle of the night.